thank you very much to the organizers for inviting me to present some of our work in this very interesting meeting. Of course, it's for me an honor. I was just in the kindergarten when the plate tectonic revolution was first presented, and I don't have much of a recollection. Actually, I went to the university, trained as a geologist, and most of our professors never talk about plate tectonics. We actually had a communist that used to talk a lot about geosynclines. So by the time I started my PhD, I was very confused about what plate tectonics really meant. But then in Barcelona, with my supervisor, who was a physicist, actually, I did learn a little bit about plate tectonics. In fact, my work, or the work with the people I have been working during these years, is mainly on tectonics. I wouldn't say it's probably plate tectonics, but it has quite a bit of significance for plate tectonics. I want to acknowledge some of these people that have been working. I mean, there is a much bigger group, but the material I will be discussing today, I've been working mainly with Ingo Geremeyer, Jason Morgan, not the senior, the junior, Alicia, Valentin Sayares from Barcelona, and quite a bit with Roland von Hune, who was the head of the department when I arrived to Geomar, and is now back in California. So this is the iconic picture from the paper from Isaacs, Oliver, and Sykes showing the subduction system, and this was based on earthquakes. And what we know is that earthquakes give part of the picture, but when mantle tomography started to play the game, we realized that some of these slabs go much deeper and go probably all the way to the core mantle boundary, these high velocities. So actually, subduction zones are very, very large scale and probably involve the entire mantle. So for this particular presentation, I'm going to be concentrating in the regions I've been more interested, and I think it's quite a bit ground to cover already in the presentation. And I will be concentrating mainly in the shallowest part of the system, where there is much of the exchange of material, fluids, and volatiles. This is a diagram of the perspective that they had of these systems at the end of the last century, basically, reviewed geophysics from Stern, showing that the downgoing slab, very simple structure, the overriding system, far more complex, far more details. We knew much more about that. So my presentation is going to be centered on three topics that I will go relatively quickly: earthquakes and slow slip phenomena. I haven't really worked too much on this, but I think this is really very important. We know that interplate boundaries, they have to be very weak for plate tectonics to work. Then I will discuss some of the work we did about fluids across the forearc, and how we are starting to speculate on the relation to large-scale deformation. And then I will discuss the incoming plates. This has been a discovery for the last 15 years. They're not as simple as we thought, and then I will go quickly into what to do to advance if I have the time. So earthquakes, they call our attention not only because of the earthquakes, because of the results, and mainly because of the tsunamis. And why tsunamis occur is still a big question. This is the diagram that was put during the revolution, in which it was pretty clear that the earthquakes were located in most of the large earthquakes in very well-defined zones. And then during the time, we realized that the earthquakes, the large earthquake, had a distribution that came into the concept of earthquake recurrence and seismic gaps. During the 90s or so, they started to do some detailed waveform analysis to learn about how the rupture actually occurred. But it was not, I would say, to the time of the largest earthquakes, the Andaman and recently the Tohoku, in which all these different approaches were starting to give similar results. And what we discovered, was to our surprise, is that when these large earthquake ruptures, they rupture in a very complex manner. Sometimes the largest slip is close to the trench. There are patches in which there is very little slip. And that was very well shown during the Tohoku earthquake, in which actually the largest slip was very close to the trench, which was quite a bit of a surprise, and that's why it produced this very large tsunami. So there have been a number of papers talking about the broken paradigms. When high quality seismological data started to be analyzed, we realized that the old ideas where the large, the gigantic earthquakes, the great earthquakes occur, they don't occur only in young plates at fast convergence because Andaman was in the slow convergence. They don't require a very smooth plate boundary with voluminous trench sediment because the Hoku-Oki actually occur on a fairly starved trench with a very rough ocean plate being subducted. And prediction and based on recurrence time is very complicated because these systems, they occur in millennia, so our record is very, very, very short. In addition to this, to the regular earthquake, this is seismic moment, and this is characteristic duration. During the last 15 years or so, it's also been discovered a whole series of new types of slip on the fault plane. These are the slow slip phenomena, many different types of phenomena, including events that last some minutes to 1 hour, that last days, months, or up to a year. And this has brought a whole new discussion on where they occur, whether they occur in the mantle, they occur at the base of the crust, some kind of mechanical transition, and they produce different type of signals as well. And this is a topic that today is pretty much under discussion, and we need to advance on characterizing these deep systems to understand them much better. One effort to do this is collecting high-quality seismic data. This is a 3D data set we collected offshore Costa Rica with the Marcus Lancet. Great effort, several millions of dollars. And then we drill the shallow part of it, and now there is a proposal that aims at drilling the deep part, like in Nankai. This is very interesting. We should be able to obtain a lot of information on fault mechanics. However, one of these projects is more than $100 million. Therefore, there will be very, very few in the near future. So, understanding the earthquake, nucleation, rupture, and propagation and arrest of these events, these large events, it means that we have to understand the fault mechanics of this entire shallow part of the plate interplate, which we know conceptually that is very complex, and we have to put that into modeling based on the deformation we measure at the surface. But to do that, we have to realize that these earthquakes, the small ones, they rupture like from 30, 50 kilometers to maybe 5 kilometers. But the ones producing the earthquakes, we know, the tsunamis, sorry, we know that they rupture all the way close to the trench. So we need to actually monitor not only the GPS information onshore, but we need to do also submarine geodesy, which is a coming field. So in relation to this, we need to understand how fluids move around on these fault systems. And we put, when I was at Geomar, we put quite a bit of an effort. We were several tens of researchers working on fluids across the four arcs. This is a side-scan sonar image. These are of Middle America. These white spots draped on bathymetry. Sorry, these are the canyons in the upper slope. And there are many of these spots in which fluids are coming out. We know that about 150 degrees or so, there is a transition from what is considered an area of deformation that doesn't accumulate elastic strain to an area in which elastic strain is accumulated. And we know that this 150 degrees is shallower than that, is the region in which there are a whole series of metamorphic and diagenetic transformations that they release quite a bit of water. And we also know, this is also again the review, this was the ideas. During the 80s and the 90s, there was quite a bit of work on the structure of four arcs, and we realized that there were accretionary four arcs and erosional four arcs. And about 50% of the world is accretional, and about 50% of the world is erosional. Accretionary systems have been somehow more studied in detail. I believe it's because simply seismic images are much nicer there. This is a profile from '73 that I reprocessed. You can see very nice structures, anticlines and thrust faults offshore valley. And therefore, these regions attracted more attention. By the end of the last century, there were many studies of the hydrological systems in accretionary prisms, and their conclusion was that, particularly venting at the seafloor, they studied and they concluded that their contribution is not apparent. And the conventional wisdom is that the hydrological systems of accretionary prisms are largely controlled by the fluids along the interplate, the megathrust earthquake. But the erosional systems are very different. There is no accretionary body, only a very small frontal prism. This is like 5 kilometers, maybe 2 kilometers sometimes. This is this unit, the form here. And the rest is a body of basement, which is actually very often cut by normal faults rather than thrust faults, in which the plate boundary is supposed to migrate gradually into the upper plate, removing material of the upper plate and bringing it into the subduction channel. So very different to accretionary prisms. When we studied them, we detected many different seafloor vent sites, and we went, and that was side scan sonar, this is bathymetry. We went and looked at them in detail with cameras. We took a lot of cores to sample the sediment and the pore water fluid in them. And then we discovered that many of them, they have abundant evidence of fluid seepage on the seafloor. They have chemosynthetic fauna, bacterial mats, all of them indicating that these are regions of active vent fluid. We also look at heat flux data. This is regional heat flux from BSR data, and we could see clearly this is one of the mounts. The numbers are heat flux measurements. We could see that the temperature, I mean the heat flux coming at the taking around this mount is clearly higher than the heat flux, the regional heat flux, indicating some kind of deep fluids coming to the surface. So what kind of fluids come to the surface? We look at that in detail. We took samples, as I say, and measured the chlorinity. These fluids have lower chlorinity than seawater, so they're fresher water. They are not seawater. They are water that is being produced by some mechanism that produce water that is fresher than the seawater. The geochemists, our colleague geochemists, they modeled that, and they concluded that they have to come from dehydration of clay, basically. So we mapped them all along Costa Rica and Nicaragua. We found 124 large seepage sites. There are many others, smaller ones, but I'm just using the big ones shown here in the map. And then we also model the plate boundary and determine the temperature at the plate boundary. This is 50 degrees, and the red line is this 150 degrees isotherm that I was mentioned before, in which, in this region, the dehydration of the downgoing sediment should be occurring. So if we look at seismic data in this region and then two more lines in here, what we see is that this is the temperature along the plate boundary. We see that between this 60 to this 150, so we have a fairly reflective plate boundary in different seismic lines. There are some reflective spots, and these spots in which you can look at the polarity. This is the seafloor, orange, black, orange. This is the plate boundary, dominantly black, orange, black. So reverse polarity. This other example is quite clear as well. This is the seafloor. This is the plate boundary. So this is reverse polarity, indicating that probably the plate boundary in this region has abundant fluids. So basically, the seismic data is imaging this region of dehydration of the subducting sediment. Our geochemical colleagues, they also model the flow rates based on the pore water chemistry and the heat flux measurements. And we put all that together in a very simple back-of-the-envelope model in which we know the input because it's been drilled, the sediment at the trench, so we know how much water is coming per kilometer of trench. We know the output at each vent site. We have the area, the average area. We have the advection, fluid advection rate. So we know more or less how much water. And we have the total number of vents. So we know there is a large vent every 4 kilometers, more or less. So very crudely speaking, we can tell that all the water that is being dehydrated or is being released by dehydration reactions along the plate boundary in this region is actually being expelled through the upper plate across fracture porosity and across this venting system, basically. So if you put all that together with the location of the large earthquakes, these are focal mechanisms of thrust earthquakes that occur on the plate boundary, we can see that all these focal mechanisms, actually, they are all deeper than this 150 degrees isotherm along the plate boundary. So basically, we came to this model in which the plate boundary in the shallow part is fluid rich. These fluids are not carried down into the deeper system, but they are actually percolating along a whole network of fractures that come to the surface along in all these different vents that we have seen. And in the deeper part, where we have this drier, not dry, because surely there will be a lot of fluid, but drier fault, then is the region in which earthquakes are actually generated or nucleated. So this is a very simplistic view, and it's still a lot to be done, but we have here a recent paper in which they show that the geodetically locked patches, actually, they seem to coincide with resistive regions in which they assume that they are fluid poor or perhaps well-drained systems, like with these fractures I was mentioning, or perhaps some basement high as well. So there seems to be a very one-to-one correlation between these two observations. But still, this has to be put together with all these different earthquake phenomena that I've been describing. So I will move now to the third topic. This is the incoming plates, subduction zones. This is a picture from Chile in which we can see the incoming Nazca plate. And we can see that the morphology changes dramatically in these 40, 50 kilometers as the plate approaches the trench axis. This brings us again to this publication from the 68 paper, in which they realized that for the time, the quality they had, they realized that the plate was actually being transformed in the sense that it was tectonically being deformed as it approached the trench axis. And in the model, they also called attention that this is a region in which earthquakes, they indicate deformation of the downgoing plate. This, however, has not attracted much attention since then, and you can see in this conceptual cartoon of what to do for the US margins program for the 21st century, what were the interesting aspects, the seismogenic zone and the very complex upper plate, but the downgoing lithosphere was basically just a line at the top and a line at the bottom. However, in 2001, Peacock called attention by proposing that thermal modeling, it could be the 600 degrees isotherm approximately, could be adjusted to the double seismic zones, proposing that these regions of dehydration of the slab due to the presence of serpentinization, but that posed a problem because these double seismic zones are fairly deep into the downgoing plate. This is very interesting because serpentinite is a very interesting mineral because, or rock, sorry, because it gives very good information. It occurs, typically serpentinization occurs below 500, 600 degrees. It can take a lot of water, up to 13%. It's very interesting because it's exothermic, so once you start it, it can go on as long as you provide water. And also it's interesting because you can detect it with geophysics because there is a considerable change in velocity from velocities above 8 to full serpentinization, about velocities of about 4.5 BP velocities, and there is a clear decrease in the density, and geologically speaking is relatively fast because the diffusion speed is about 1 kilometer per million year at about 300 degrees. It's also very interesting because if you are, if serpentinization occurs, serpentine is stable to great depths. Actually, can, depending on the path of the slab, it can provide water at relatively great depths of over 100 kilometers, or may even go in very cold slabs into phase A and carry water deeper in the system. So there was a debate in the 2002 came out this paper on serpentinite seduction, in which in science, yeah, in which seductive but extremely unlikely, difficult to reconcile with hydraulics, and the large increase in rock volume accompanying serpentinization should stop the process. And I think that was the view of many people at the time. So the serpentinization may occur at the mid-ocean ridges, but it was very unlikely in the outer ice. So about that time, we were collecting, actually, mostly looking at the overriding plate in Middle America, but we had the luck to hire an industry ship, high-quality seismics equipment, and we were shooting data in the region, and we decided to shoot 2 lines going across the trench axis, which we rarely did, and well into the incoming plate. That was a bit of serendipity, I should say. So what we found, it was, to our surprise, the 2 seismic lines, they show very clear dipping reflections going deep into the system, and clear mohole reflections as well, so we know many of them are in the mantle. You can trace some of them, and you can map them here, and you can see that they are fairly large. They're like 60 kilometers faults. You can trace that one too. You can map it here. This is some 40, 50 kilometers long. So they are pretty large faults, actually. Also, if you look at the normal faults, looking at the basement, there is a lot of mass wasting going on the surface, so the structure is very complicated here and is distorted by the mass wasting process of the sediments. By mapping the top of the basement, you can see that the number of faults increases as you approach the trench axis, and also the cumulative offset of these faults is increasing. So quickly we look back in our archive, and we found some older wide-angle data. We modeled it in the Chile Trench, and we discovered that not only the crust produced by the fracturing, but also the mantle, they seem to have low velocities. We published that 1 year after. And then we collected heat flux data. This is the heat flux that was suspected. This is the ocean plate. So we see that the ocean plate the heat flux line was here. The ocean plate has very low heat flux in this particular trench. And when you look at this in detail, actually, when you look at this region in detail, what you can see is as the faulting increases in the very close proximity of the trench, the heat flux rapidly decreases, indicating that there is active percolation of water into the system. So since then, there's been a wide angle taken across trenches in many regions of the world, well into the oceanic plate, and basically all of them, with the exception of the very hot, very young Cascadia system, they have found very low velocities in the mantle. This is a compilation which is published in Geosphere a couple of months ago, in which we look at all these different experiments in different trenches of the world, and we can see that as you approach the trench axis, the velocity in the mantle and the velocity in the crust is decreasing. But of course, the burning question is decreasing of the velocity fracturation caused by fracturation, or is caused by serpentinization? Well, we look at this data. We also model not only P-wave velocity, we model also S-wave velocity. And if you do that, and it's a longer explanation, but if you do that by looking at VPS-VS ratios, you can demonstrate, basically comparing to laboratory data, that the velocity we have in the mantle, in the trench, are more appropriate for serpentinized mantle than for a mantle that is fractured with no fluids in it, basically. So the proposition that we made then is that the conventional model was assuming that most of the water carrying in slabs was in the basaltic pillows, in the seated dikes and gabbros. So in the crust, what we propose is that actually we should take into account the mantle because a lot of the water could be there. So by assuming a 15% serpentinization in a 15-kilometer thick mantle column, we can calculate that the water contained here is much more than the water that could be contained in the crustal section. And that brings us to the conceptual model in which the downgoing plates, they have also a complex structure, they are highly deformed in the trench, they are highly chemically modified and mechanically modified, and they carry down water to great depths. Probably colloquitization of the crust is involved in shallow water release, and this serpentinization may be involved actually in the water at about the right depth to produce arc volcanism. This has attracted some attention. Soon after we published that, Manuel Facenda showed that some of the anisotropy that is observed under subduction systems could be produced by the serpentinization along by the anisotropy produced by the serpentinization of the faults in the downgoing plate, and he also modeled the variation in tectonic pressure that will permit the water to go deep, is shown here in red, deep into the system. And this has brought into the discussion how deep this water can remain into the slabs. There's been some propositions based on the distribution of earthquakes and VP velocities that they propose that the water should not go below about 400 kilometer depth, and they should be released before going into the lower mantle. More recently, modeling of waveforms, actually, they propose that they can see that the slab contains water all the way down to deeper than 600 kilometers, and therefore that it could bring this water down into the lower mantle. And also looking at the geochemistry of mid-ocean-rich basalts, there's been the recent proposition. This is from 2017, that the Earth's mantle is highly processed, and most of this water were introduced by subduction of serpentinized lithospheric mantle and associated dehydrated crust, basically. So, but actually, in addition to that, in parallel to our work, there has been some growing evidence that the incoming plates are transformed at actually a much larger scale. It's not only constrained to trenches, but probably occurs across the entire outer ice. There's been the discovery, now 10 years ago, was published that there were a number of small volcanoes found away from the trench in this Cretaceous ocean plate, that these volcanoes were actually quaternary, the so-called petite spot volcanoes, and therefore that they represent some form of release of melt from the asthenosphere across the entire overriding plate. And more recently, it's been proposed that they're probably associated to important metasomatism at the base of the incoming plate. So it seems that we have to start thinking of systems in which not only the upper plate is complex, also the incoming plate, and not just near the trench, but actually possibly at the much larger scale, not just 100 kilometers, but probably 300, 400 kilometers. I'm just finishing. So the significance is that the incoming plate subduction trenches are systems that are at least of the dimension of the mid-ocean ridge, and therefore are a new class of geodynamic settings in themselves that we should study in detail. What to do with the next? Do we have 2 minutes? Yeah, okay. What to do with, how to progress next? I think it was mentioned yesterday that the data were very important during the plate tectonics revolution. I would say that it's not just a matter of obtaining more observations. I would say that it's a matter of having new technologies as well. During the plate tectonic revolution, a key aspect was the development of flux gauge magnetometers, echo sounders to map the seafloor, and the post-war seismological network. The advancements in seafloor mapping were relatively slow. In 70 years, they went from this map to this map, in which they started to trace the mid-ocean ridge. But then, in about 20 years, we went into this type of structure in which the mid-ocean ridges, this is a later compilation, but the mid-ocean ridges were very well defined during the 60s. And then in the 80s, we had a far more realistic map. Today, we even have much more detailed images of the processes that occur in subduction systems. And all this is not just data collection, it's development of new technologies. So I would say what we need to do is a new generation of geophysical tools. This new generation will imply that these images, which are recent work, in which the resolution is basically as you go deep into the system, on tens to hundreds of kilometers, we have to move from these images, in which this is the base, this is the state of the art today, to something that is starting to look at boundaries which we know they exist for instance, under the forearc, in which they've been mapping all these different complicated reflections. So we need to define new tools. We know, for instance, pre-stacked migration was a great tool that's been used by oil industry. Travel time tomography offers a low-resolution image of physical properties, and recently, full waveform inversion is becoming a more and more advanced tool that is starting to provide physical properties, VP velocities, or other properties that is starting to look more as the real world, more the resolution that we got with seismic reflection methods. So we probably need to move to also cheap systems like OBSs, large-scale deployment of OBSs that will allow to collect new forms of data that should provide new types of observations, not just new observations, but new types of high-resolution observations. So in summary, I think these are three topics that are really worthwhile thinking about them for the 21st century, if you will. This is how the interplate fault behaves in terms of mechanics, fast earthquakes, slow slip phenomena, how the fluids are distributed, and how they relate to all these phenomena. Incoming plate, we should look more carefully to the incoming plate because it has great significance, and to the slab structure, and we should think how to develop to promote the development of new technologies. This is a very slow process, very difficult in today's very competitive world to obtain funding. And I think that's all. Thank you.